So here's your notes. I'm going to do the PowerPoint little dealie again. I'll make it nice and I'll make it as big as I can. Again, if you can't see somewhere from the back, just let me know and we can temporarily move you further forward for the notes part, and then you can sit back for the lesson part. I thought I'd made these big enough, but it's kind of tough to guesstimate what it looks like. My screen changes when I plug my projector in, so sometimes my guess of how big it looks in real life isn't quite what it is. Resistance and one of the fundamental laws of circuits, Ohm's law. So it turns out, as electrons travel through a load, remember we used that term last day, we said a load is what absorbs the energy from the electrons. They encounter resistance, usually just by running into other electrons and other atoms, so they encounter resistance, which slows them down and causes their energy to be transformed into heat and light and stuff. Have very low resistance, so you don't want to lose much energy to wires. In real life, Candace, you do actually lose energy to wires, which is why when you're building a circuit, you do want to keep the wires as short as possible. If you have a bunch of extra wires, you don't just coil it up and clip it to the end, you cut it out of the circuit. But we're going to pretend, for our sakes, that wires have no resistance, otherwise the math gets yucky, the physics gets yucky. And that's done almost all the time in circuits. But lights have high resistance. The greater the resistance, the more work done. And you can, if you want to, put in brackets, usually more heat. From the same idea, Omid, for the same reason, really, that when you rub your hands together and create friction, it generates heat. If you have high resistance, it's hard for the electrons to go through. They bump into other stuff. They cause the atoms they generate heat. So all a light bulb filament is, Kiana, is a high resistance piece of something. I'll get into that another time. But it's so high resistance that it glows white hot. It generates that much heat. And that's why when you touch a light bulb, you burn your hand. These, the fluorescent ones, are a very different type of technology. Actually uses quantum phenomena. That's another show. Every circuit offers some resistance. You know what? We're going to use a symbol for resistance, capital R for resistance. And from now on, if you see a capital R, or if you want to write the word resistance and you use a capital R instead, I'll figure it out. I'll figure it out. Not a lowercase r, though, an uppercase R. Every circuit offers some resistance to the flow of charge. The circuit symbol for a resistor is a short series of angled lines. All a resistor is, Matteo, any type of a load. iPod, light bulb, electric motor, kettle, stove, washing machine, whatever. We don't want to have separate symbols for every appliance out there, so we have a generic symbol for a resistor. It's a series of angled lines. I wrote, write the symbol for resistor, write the symbol for resistor there. So it says, write the symbol here in your notes. Wire, resistor. You can do it neater than I just did, but I'll figure it out. Okay? Okay. The resistance, it turns out, is due to electric friction, where electrons collide with the atoms of the material that they are passing through, which causes them to lose energy. This energy lost by the electrons heats up the material they are passing through. And Candace, we're very clever with what we can do with that heat. How clever? Well, this clever. Right? Your smartphones essentially work from that. We bleed that heat off, and we can do stuff with it. It's a little more complicated than that, but that's where it all started. Certainly a light bulb is a great example of friction, heat, light. Yep. Somebody at the door? Hang on, let me hit pause. That's cool. Let me still hit pause. Oh, where's my... Oh, it's okay. I'm doing a lesson, not cool stuff, so they can go elsewhere. They'll come back next block during my prep because I'll bring out all my physics toys. Hey, attention span here now. Squirrel! No, here. I know. Are they wanting to come in, though? They're just walking out there, right? So a loss of energy implies a loss of voltage. A loss of energy implies a loss of voltage. A voltage drop across the device. In other words, in a circuit, if the current is going this way, Kiana, if you have a higher voltage here, you'll have a lower voltage here. If I was making up numbers, let's suppose, is my pen working? My pen just decided to stop temporarily, so let's pause the video. I've been having... So as an example, you can think to yourself, guys with me? Guys? I need you to focus here. No, when I say I need you to focus here, it really means I need you to focus here. So let's suppose right here we had 6 volts. And let's suppose right here we had 1.5 volts. Can you tell me how many volts must we have lost in that resistor? Do the math. 4.5. It's straight adding. Okay? You must have lost this. So if you put up, remember the voltmeters we played with? If you put one on either end of this resistor, it would measure 4.5 volts. By the way, technically, because you lose it, but we know that you lose voltage in a resistor all the time, so over the years we've gotten lazy and we've just stopped writing the negative. We've said it's a voltage drop, clue in. Okay? We're going to start eventually labeling circuits along the way. You don't have to put a negative on any resistor, but you do need to know you're losing voltage. The amount of flow, or current. Okay, you guys are just going to have to follow along because my pen has decided to stop working. Current, that word right there, through the circuit depends on the total amount of resistance and on the voltage applied. This is Ohm's law. This is Ohm's law. So remember, I gave you the following analogy. I said voltage is like the height of a hill. You can write this down if you want, or you can just watch. It's up to you. You got kind of room at the bottom of the page there. Current is like the number of skiers. Resistance is like the depth of snow. Higher resistance is like a ski hill that has deeper snow. You can't go as fast. Lower resistance is like a ski hill that has faster snow. You can go shallower snow. You can go faster. So I wrote down here. I'll wait. So here's our analogy. I'll come back to that in a second. So what can be said about the current flow in each case? Fill in either large current flow or small current flow. If you have a high resistance, if the hill is really, really slow, can you get more skiers on there or less skiers on there? Well, you can only fit a few skiers on there, otherwise they'll bunch up. So a high resistance actually means smaller current. A low resistance means a higher current. What about a high voltage? Now I told you voltage was like the height of a mountain. What's more popular, higher chairlifts or small piddly lower chairlifts? Higher voltage is going to mean more skiers. And lower voltage means smaller current. So here's what really happens. As resistance increases, current decreases. When one goes up, the other goes down. Another way to think about this is to imagine that current is like students running through the hallway, and resistance is like the number of other kids in the hall. If the hallway is empty, we can run lots of current, lots of students through the hallway. If the hallway is crowded, you can get 1 or 2 kids through at a time. Higher resistance, lower current. Lower resistance, higher current. Now we're actually going to do this, Omid, mathematically. I always introduce it first in terms of English and concepts, but we're actually going to have an equation that describes all this called Ohm's law, and it's why I gave you your yellow formula sheet today. Resistance slows down the flow of electrons, which allows the load, the light bulb, the iPod, the stove, to convert the electrical energy into other forms. And key ideas, resistance, the units for resistance is ohms. And it has a funky symbol. It's a Greek letter, omega. Why didn't we use a letter O as our symbol for ohms? Because what number does an O look like? We don't need that confusion, okay? So we have now the abbreviation for voltage, capital V. The abbreviation for current, what was current measured in? Do you remember? You're close. I kid you not. She went amps, symbol capital A. And this resistance is measured in ohms, symbol, looks like a little mouse hole in a wall if you want to think about it that way too, omega. So, okay, what is resistance exactly? Well, okay, it's the property of matter that resists the movement of electrons. It's crowdedness. So it can be thought of as a form of friction slowing down electrical flow in a circuit. I see some yawns. Put your pencil down. Look up. This has nothing to do with actually what we're looking at in physics, but it's pretty cool. Keep going. What can affect electrical resistance? And I wrote down here, I guess for you guys, it's turn the page. Here's a diagram. Here are, count them, 4 straw setups. If you were trying to suck up liquid through these straws, or even just breathe air through these straws, which of these do you think would be the easiest to breathe through? 1, 2, 3, or 4. We'll call them, you know what? Let's be really, really, really clever. Let's call them A, B, C, D. Well, you know what? Let's ask this. What do you think would be the toughest to get air through? Okay, so let's write down next to here, highest. What's a capital R the abbreviation for? I don't feel like writing it. Go ahead, okay?
Is that right?
Yeah. Why is that tough to get air through? Because there's kinks. One of the things that increases the resistance of wire, the thinner the wire, the higher the resistance is going to be because there's just not so much. You know what? The thinner the hallway, the fewer students, the fewer current you can get through there. Okay? Which of these do you think would be the easiest to suck air through? You could get lots of air through 3 straws as opposed to 1 straw. In terms of our wire, oh, you know what? This is why sometimes in a circuit we'll put several wires. In fact, what we'll actually do, Amelia, is we'll braid a bunch of wires together to make them thicker. The thicker the wire, the less resistance. That's why for really, really high power appliances like your stove, if you pull your stove off from the wall and you look back there, you'll see the wire is really, really, really thick. Because it has to be, it's taking a lot of power. Okay, what's next, do you think? A or D? Sorry, I wasn't clear. Which would be the next toughest to drink water through or get air through? D. So also, I'm going to say second highest R. And this Candace, I think I mentioned a few minutes ago, this is why we try and make our wires in our circuit as short as possible, both to save material, to save money, but also a longer wire has more resistance. I used to, before we had Wi-Fi in this room, I used to actually run an Ethernet cable up the ceiling, all the way over here and down. And you may even see in Miss Kim's room, Mr. Chu's room, I think there's still a cable doing that. There's a couple, and I think Mr. Perugia might even have a cable doing that. That long cable dramatically slows your Ethernet speed, your internet speed, because it's just more resistance. Dramatically slows it. But if it's all you got, because there's no connection nearby, okay. I have one long cable plugged into my phone back there, but it slows down my internet speed, more resistance. What does resistance depend on? How long the wire is, and ready, here's your fancy word, the cross-sectional area. Bigger area, lower resistance. Shorter wire, lower resistance. Does that make sense? So, in high resistance, electrons tend to move more slowly, which means they're going to give off more heat. A high resistance wire will heat up, and I think I mentioned this the other day, but if I didn't, I'll say it now. Your stovetop elements are simply a controlled high resistance short circuit. They heat up red hot, which in that situation is fine, but hey, if you're wondering why do houses burn down when they say it was an electrical fire, almost certainly what happened was a wire was asked to handle more resistance than it was rated for. More current than it was rated for, and because it had a high resistance, it glowed red hot and touched some of the wood in the house and fire burned. Oh, so they lose more voltage, right? Low resistance, electrons move faster, they give off less heat energy, and they lose less voltage. Kiana, the holy grail is what's called zero resistance. We have a fancy word for that. We call them superconductors. Superconductors, and we have some. There are these very bizarre substances that have no resistance, which means if you make them into a circle and you start some current going in that circle, it'll keep going until the end of the universe. Keep going and going and going and going. You lose you lose no energy to outside sources. So we found superconductors, I think the first one we found was in the 1940s. But it only worked at very, 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 very cold temperatures, about 5 degrees above absolute zero, which is crazy cold. But in the 1960s, we found superconductors that you can cool with liquid nitrogen. Liquid nitrogen, we can bulk manufacture. So stuff that I can't do here, but if you go to universities or if you ever go to like an engineering open house at UBC or SFU, almost certainly they'll bring out the superconductors. I'll show you a very cool video about some of the strange, bizarre properties that superconductors have. The problem is liquid nitrogen, Aiden, is still kind of expensive. If you want to win a Nobel Prize, if you want to be able to buy Bill Gates someday, if you want to be the richest person on the planet, if you can find a room temperature superconductor, that would completely revolutionize all of our electric infrastructure. Every bit of it. A little bit more. Here it is. Ohm's law. Ta-da! This is the relationship, the mathematical equation between current, voltage, and resistance, where V stands for voltage. Sadly, C does not stand for current, and the reason is C stands for coulombs, and C was taken by something else, so we went to a Latin word that means current flow. We use I for current, which means anytime you write a capital I, I'll clue in you mean the word current, I'll figure it out. And R stands for resistance. Put your pencils down.